Welcome to the final section of Chapter 3 of Principles of Mathematical Analysis. We close our study of series with a question that sounds almost silly. If we add up the same numbers in a different order, can the answer change? For finite sums, the answer is obviously no. For infinite series, the answer is one of the most surprising facts in all of analysis. We will see a concrete example where reordering changes the sum, then prove Riemann's rearrangement theorem, which says that a conditionally convergent series can be rearranged to do essentially anything we want. Finally, we will prove that absolutely convergent series are completely immune to reordering. Let's dive in. Here's the plan. We start with some motivation, contrasting finite sums, where order never matters, with infinite series, where the order of the terms is built into the very definition of the sum. Then definition 3.52 makes the notion of a rearrangement precise. Example 3.53 gives a concrete rearrangement of the alternating harmonic series that converges to a different value. The centerpiece is Riemann's rearrangement theorem. Theorem 3.54. A conditionally convergent real series can be rearranged so that its partial sums have any prescribed upper and lower limits. We then prove Theorem 3.55, which says absolutely convergent series can be reordered freely, and we finish with a summary of the section and of the whole chapter. Let us begin with the basic question of this section. Does the order in which we add numbers matter? For finite sums, certainly not. Addition is commutative and associative, so any reordering of finitely many terms produces exactly the same total. This is so familiar that we never think about it. The surprise is what happens when we pass from finitely many terms to infinitely many. But an infinite series is not just a bag of numbers. By definition, its sum is the limit of the partial sums, and the partial sums are formed by adding the terms in a specific order. First a sub 1, then a sub 2, and so on. Change the order of the terms and you change every partial sum. Hence, you change the sequence whose limit defines the sum. There is no obvious reason the new limit should equal the old one, or even exist. So we face two natural questions. First, if a series converges, does every reordering of it still converge? Second, if a reordering does converge, must it converge to the same sum? The answers form a beautiful dichotomy. For series that converge absolutely, reordering changes nothing. For series that converge only conditionally, reordering can change everything, and Riemann's theorem will tell us exactly how badly. First, let us make the idea of reordering precise. Here is the precise definition. A rearrangement is described by a sequence k sub n in which every positive integer appears exactly once. In other words, a one-to-one function from the positive integers onto the positive integers, a permutation. The new series has term number n equal to a sub k sub en. The phrase once and only once is the heart of the matter. It guarantees that no term is dropped and none is repeated. So the rearranged series really is built from the same ingredients, just served in a different order. That is exactly what makes our question a fair one. Let us draw a picture of this. The picture shows what a rearrangement does. The blue boxes on the top row are the original terms in their original order. The amber boxes on the bottom row are the rearranged terms. Here, a prime sub 1 is a sub 2, a prime sub 2 is a sub 5, and so on. Each colored arrow traces a single term down to its new position, and the crossing of the arrows is exactly the shuffling. The caption records that the index sequence K sub n is a bijection, a permutation, so every box is used once and only once. The line at the bottom records the key consequence. The partial sums of the two series consist, in general, of entirely different numbers. A concrete example will show that things really can go wrong. Here is the classic example. Equation 22 is the alternating harmonic series. 1 minus 1/2 plus 1/3 minus 1/4, and so on. It converges by the alternating series test, theorem 3.43, but it does not converge absolutely, since the harmonic series diverges. Equation 23 is a rearrangement of it. We take two positive terms, then one negative term, and repeat. So it starts 1 plus 1/3 minus 1/2, then 1/5 plus 1/7 minus 1/4, and so on. Every term of the original series appears exactly once. We will now show that this innocent-looking reshuffle changes the sum. First, we pin down the true sum of the original series, called S. We will need it as a benchmark to compare the rearrangement against. Group the series the way the slide does. The first three terms add up to exactly 5/6. Everything after that falls into pairs. Minus 1/4 plus 1/5, then minus 1/6 plus 1/7, and so on, and each pair is negative because its negative term has the larger absolute value. So S is 5/6 plus a whole string of negative corrections, which forces the boxed conclusion, S is strictly less than 5/6. Hold on to that number, and let us turn to the rearrangement. Now look at the rearranged series in blocks of 3. 2 positive terms, then 1 negative. The slide shows that every such block, the k-th one, is positive. Here is why. Both positive fractions in the block are larger than 1/4k, so the two of them together exceed 1/2 gege, which is exactly the negative term being subtracted. The positives win, and each block contributes a net positive amount. So the running total, taken right after each complete block, keeps climbing, forming a strictly increasing sequence, and the very first of these totals already equals 5/6. Intuitively, serving 2 positive terms for every negative one front-loads the positive mass and props the sum up. Putting the two steps together, the upper limit of the rearranged partial sums is greater than S prime sub 3, which equals 5/6, while the original sum, S, is strictly less than 5/6. So the rearranged series certainly does not converge to S. As the remark notes, the rearrangement does still converge. Rudin leaves the verification to the reader. As a piece of extra insight beyond the book, the original sum is the natural logarithm of 2, about 0.69, and the rearranged sum is 3/2 times the natural logarithm of 2, about 1.e4. Reordering inflated the sum by exactly 50%. A picture makes this vivid. This plot shows the first 12 partial sums of both series. The blue dots are the partial sums of the original alternating harmonic series, equation 22. They oscillate and squeeze down toward the blue dashed line at the natural logarithm of 2, roughly 0.69. The red squares are the partial sums of the rearrangement, equation 23. Same terms, but because 2 positive terms arrive for every negative one, the red sequence settles around the higher red dashed line at 3/2 times the natural logarithm of 2, roughly 1.04. The two series use identical ingredients and converge to different sums. Riemann turned this observation into a spectacular general theorem. Here is the remarkable theorem, due to Riemann. Take any series of real numbers that converges, but not absolutely. We call such series conditionally convergent. Pick any two extended real numbers, alpha and beta, with alpha less than or equal to beta. They are even allowed to be plus or minus infinity. Then there is a rearrangement of the series whose partial sums have lower limit exactly alpha and upper limit exactly beta. In other words, by merely reordering the terms, we have total control over the limiting behavior of the partial sums. The hidden reason this works, which the proof will make precise, is that a conditionally convergent series secretly carries an infinite amount of positive material and an infinite amount of negative material. We simply dole them out in whatever proportion steers the sum where we please. Let us spell out what this freedom buys us. Let us unpack the statement, one choice of alpha and beta at a time. If we choose alpha equal to beta equal to some number, the rearranged partial sums have the same lower and upper limit, so the rearrangement converges, and it converges exactly to that number. In other words, by reordering alone, we can make a conditionally convergent series add up to any target we like, and that is only the first option. Second, the targets are allowed to be infinite. Choosing alpha and beta, both equal to plus infinity forces, the partial sums to march off to plus infinity. So the rearranged series diverges. Choosing both equal to minus infinity sends it to minus infinity instead. A convergent series has been reordered into a divergent one. There is one more behavior on the menu. Finally, if alpha is strictly less than beta, the partial sums settle into permanent oscillation, dipping arbitrarily close to alpha and climbing arbitrarily close to beta forever. So conditional convergence is extremely fragile. The sum of such a series is an artifact of the order of its terms. Now, let us see how the proof achieves all this. Before the formal proof, here is the high-level plan. Step 1 is the key structural fact. In a conditionally convergent series, the positive terms alone form a divergent series, and so do the negative terms. This gives us two infinite reservoirs, one that can push the partial sums up as far as we like, and one that can pull them down as far as we like. Step 2 picks finite targets, alpha sub n and beta sub n, marching toward alpha and beta. Step 3 is a greedy construction. We alternate between the reservoirs, each time taking just enough terms to cross the current target. Step 4 explains why this works. Each overshoot is at most the size of the last term used, and the terms of a convergent series tend to 0, so the overshoots vanish. Let us carry this out. We start by splitting each term into a positive part and a negative part. The quantity p sub n is the positive part. It equals a sub n when that term is positive, and 0 when the term is negative. The quantity q sub n is the size of the negative part, 0 when a sub n is positive, and the absolute value of a sub n when it is negative. The two formulas on the slide, written with absolute values, are just a compact way to say exactly that. From them, we read off the identities. The difference of the parts recovers a sub n. Their sum recovers the absolute value, and neither part is ever negative. Next, we show that both of these series diverge. Now the crucial claim. The series of p sub n and the series of q sub n must both diverge, and each hypothesis rules out one failure mode. If both converged, their sum, the series of absolute values, would converge, contradicting that our series is not absolutely convergent. If exactly one converged, look at the identity on the slide. The partial sum of A sub n is the partial sum of the P terms minus that of the Q terms, so the series of A sub n would diverge, contradicting convergence. Conditional convergence is exactly the sweet spot where both reservoirs are infinite. Step 2 tidies up. Let capital P sub 1, capital P sub 2, and so on list the non-negative terms of the series in the order they occur, and let capital Q sub 1, capital Q sub 2, and so on list the absolute values of the negative terms, also in their original order. These are the same series as the P and Q series from step 1, except that the interleaved zeros have been deleted, so they still diverge. Think of the capital P terms as an inexhaustible supply of upward pushes, and the capital Q terms as an inexhaustible supply of downward pulls. With both reservoirs in hand, we can describe the rearrangement itself. Step 3 is the heart of the proof. First pick ordinary real sequences alpha sub n converging to alpha and beta sub n converging to beta, with alpha sub n below beta sub n and beta sub 1 positive. These are finite stand-ins for targets that might be infinite. Now build the series in equation 25 greedily. Take positive terms in order just until the running sum first exceeds beta sub 1. That defines m sub 1. Then take negative terms just until the sum first drops below alpha sub 1. That defines k sub 1. Then push up past beta sub 2, down past alpha sub 2, and so on forever. Each stage is possible precisely because both reservoirs diverge. Enough upward pushes will cross any bar. Enough downward pulls will sink below any bar. Since every term is used exactly once, equation 25 is a rearrangement of the original series. Here is the picture to keep in mind. In this diagram, the horizontal axis is the position along the rearranged series, and the zigzag path tracks its partial sums. The red rising segments are stretches where we add positive capital P terms, climbing until the path crosses the upper red, dashed line at beta. Each crossing is a red dot, x sub 1, then x sub 2, then x sub 3. The blue falling segments are stretches where we add the negative capital Q terms, descending until the path crosses the lower blue dashed line at alpha, at the blue dots y sub 1, y sub 2, y sub 3. Now look at the faint shaded triangles poking just above beta and just below alpha. Those are the overshoots, and they clearly shrink as we move to the right. That shrinking is the whole game, and step 4 makes it precise. Step 4 measures the overshoots. Let x sub n denote the partial sum at the top of the n-dash climb, the one ending with the term capital P sub m sub n, and let y sub n be the partial sum at the bottom of the n-dash descent. Here's where minimality pays off. Since m sub n was the smallest index that pushed the sum past beta sub n, the sum just before the final step was still at or below beta sub n. So the overshoot of x sub n beyond beta sub n is at most that single last term. The same reasoning bounds y sub n near alpha sub n. Now the original series converges. So by theorem 323, its terms tend to 0, and hence both capital P sub n and capital Q sub n tend to 0. The overshoots are squeezed away. X sub n converges to beta, and y sub n converges to alpha. One last check remains. We know the turning points converge to alpha and beta, so alpha and beta are subsequential limits of the partial sums. Could there be others beyond them? No. Between consecutive turning points, the partial sums move monotonically. Climbing during a block of positive terms, falling during a block of negative terms. So every partial sum is trapped between a nearby y value and a nearby x value, and in the limit, nothing can escape below alpha or above beta. Therefore, the lower limit of the partial sums is exactly alpha, and the upper limit is exactly beta, which is equation 24. And the proof is complete. After this chaos, the next theorem restores order. Here is the positive counterpart, theorem 3.45. If a series of complex numbers converges absolutely, then every rearrangement of it converges, and all rearrangements converge to the same sum. Note 2, upgrades compared with Riemann's theorem. The terms may now be complex, not just real, and the conclusion covers every rearrangement at once. The contrast at the bottom of the slide summarizes the dichotomy of this section. For conditionally convergent series, rearrangement can produce any behavior whatsoever. For absolutely convergent series, the order of the terms is completely irrelevant. The proof is short and elegant. It rests on the Cauchy criterion. Take any rearrangement with partial sums s prime sub n. Fix a positive epsilon. Since the series of absolute values converges, the Cauchy criterion, theorem 3.22, applies to it. There is an index capital N, beyond which every finite block of absolute values, from index n up to index m, adds up to at most epsilon. That is equation 26 on the slide. In words, the total mass of the tail beyond capital N is tiny, no matter how many tail terms we grab and in what order. This is exactly the kind of control that conditionally convergent series lack. Now we put it to work. Since the rearrangement uses every index exactly once, we can pick P so large that the first P rearranged terms include all of A, sub 1 through A, sub capital N. Now compare the two partial sums for any n beyond P. Both contain that entire head. So in the difference, the head cancels completely. Whatever survives is a finite collection of terms with distinct indices, all larger than capital N. And by equation 26, their combined size is at most epsilon. So the two partial sum sequences eventually travel within epsilon of each other. Since S sub n converges, S prime sub n converges to the very same sum. The proof is complete. Let us review what we covered. A rearrangement, definition 3.52, uses exactly the same terms as the original series, each exactly once, but visits them in a different order given by a permutation of the positive integers. Example 3.53 showed this is not a harmless operation. Taking the alternating harmonic series and reordering it so that two positive terms precede each negative term produces a series whose partial sums eventually exceed 5/6, while the original sum lies below 5/6. Same ingredients, different sum. Next, the two main theorems. The dramatic result is Riemann's rearrangement theorem, theorem 354. For a real series that converges but not absolutely, the positive and negative parts are both divergent reservoirs, and a greedy construction lets us steer the partial sums across any pair of moving targets. The conclusion: any prescribed lower and upper limits, alpha and beta, can be achieved, so such a series can be rearranged to converge to any number we like, to diverge to either infinity or to oscillate between any two bounds. The sum of a conditionally convergent series genuinely depends on the order of its terms. The final takeaway is Theorem 355, the antidote to all this chaos. If a series converges absolutely, then every rearrangement converges, and all of them converge to the same sum. The Cauchy criterion makes the proof almost effortless, because the head of the series cancels in the comparison, and the tail has small total mass regardless of order. This completes the dichotomy, and also completes Chapter 3, our study of numerical sequences and series. In the next chapter, we put sequences to work on a new subject, continuity. We will define limits of functions between metric spaces and connect continuity with the compactness and connectedness of Chapter 2. See you there.